cloud. So welcome everybody to the February 19th Evansville Astronomical Society Zoom presentation. Tonight we have a very special guest with us, and I'm just going to hand it over to our program chairman, Mr. Chuck Allen, to kick off the meeting. Thank you.
Okay, thank you, Tony. Our guest tonight is Dr. Caitlin Ahrens, and she is a NASA postdoctoral fellow at the NASA Goddard Space Flight Center in Greenbelt, Maryland. And she is working now on the remote sensing of ices, my guest particularly on the moon and some other worlds in the solar system. She studies the composition, phases, and thermodynamics of ices at the lunar poles and the surfaces, as I said, of other satellites in the solar system and planets as well. Caitlin received her BS in both physics and geology at the West Virginia University in 2015, and received her PhD in the University of Arkansas Space and Planetary Science Center in 2020. And she did her dissertation on ice mixtures under Pluto simulated conditions and the implications that those studies had for geophysical processes. Before receiving her doctorate, she was a research experience undergraduate for the U.S. Geological Survey in Flagstaff, Arizona. And for 5 years, she served as a teaching assistant and research associate at the Arkansas Center for Space and Planetary Science, where she received her PhD. She's currently doing a lot of work on, as we probably discussed a few moments ago, using the Lunar Reconnaissance Orbiter Diviner data to determine the stability of ice phases at the lunar poles. This has a lot of significance, as I'm sure she'll cover, for possible permanent stations on the moon. She studies the distribution of reservoirs of volatile substances near the lunar poles, and I'm sure on other worlds as well. And she identifies methods for determining the extent to which human visitation to other worlds may contaminate samples that are taken there. I'm interested to note that 10 years ago or 11 years ago, she received one of the Astronomical League's service awards, the Horkheimer-Doria Service Award. So I was very happy to see that as well. And tonight she's going to speak to us about space volcanoes and basically ice geysers on some worlds. As you know, they have been detected on Enceladus and Europa, possibly Mars and South Pole and Triton as well. So at this point, I'll turn it over to Caitlin with my great appreciation for your taking the time to join us tonight.
Thank you all so much again for having me here tonight. Whenever Chuck and I were discussing topics for all of you fine folks tonight, we came to the conclusion of space volcanoes, which is definitely my lovely cup of tea that I like to study. And the thing about space volcanoes, and I'll certainly go through this with my presentation here, is that there's still a lot of work to do. So whatever I show you guys here tonight is certainly just barely scratching the surface on volcanoes on other planets and certainly moons as well. So there's certainly still a lot of mysteries out there with space volcanism. So hopefully my screen sharing will work. Maybe. There we go. All right. Can you see my presentation? Awesome. All right.
It's perfect. Yes.
Thumbs up. Yay. Awesome. Okay. All right. So let's dive into space volcanism. So we're going to go through the basics though. What is a volcano? So typically a mountain or a hill, usually of some sort of elevation, somewhat conical, but that's not always usually the case on other planets, but I'll show you that here later. But some sort of elevation typically helps. Somewhat having some sort of a crater or a vent, in which case some sort of fluid, lava, rock fragments, hot vapor, gas of some sort would have had to erupt out of this vent of some sort onto a crustal surface. So if I were to ask you to draw a volcano, most of you would probably draw something like this. So this is my wonderful clip art that I did this morning. So typically, whenever I ask people to draw a volcano, it would be some sort of elevated mountain of some sort, usually flat at the top. Lots of fire dynamics, maybe some smoke going on here, maybe some lava trails going down. So we typically think volcanoes as being just very active, fiery, smoky, bubbly mountains kind of deal. And sometimes that's the case in space, but not usually. But in reality, volcanoes on Earth can take all sorts of shapes and sizes, different kinds of dynamics, certainly bigger dynamics than others, such as Mount St. Helens there. We have smaller vented volcanoes as well. So we can have what we call flavors of volcanoes. We can have different flavors of volcanoes. And like I said, all different shapes and sizes, but you have almost like a cookie cutter definitions of certain volcanoes. So we're going to jump into cinder cones. So cinder cones are very, very simple forms, very conical shape, built from congealed lava ejection. So they're very soft usually with the material that they're used. Sometimes you can have mud volcanism compared with cinder cones as well. They're very gas charged, so you usually don't see too much hot lava with these. It's more of a gas ejection kind of deal. Cinders are just rock fragments, and like I said, bowl-shaped as well. So lava domes, also relatively small. They're just piles of lava. They're just rock rubbles, very loose. They can expand from the within and then outward kind of deal, but they don't really expand that much. I'd say under 5 kilometers. So it's really quite small in that regard. But now we get into some of the bigger stuff though. So composite volcanoes, also called stratovolcanoes, very steep sided. They're usually pretty symmetrical. Lava flows have breaks or fissures that go through the center and then outward. And those central lava tubes inside are called ribs or ribbing. Whenever you have the outer shell of a volcano that has collapsed or has eroded away, sometimes those ribs can still be shown. A lot of ribbing could actually still be shown with Devil's Tower, if any of you guys have seen Devil's Tower before. There is sometimes an underground conduit system called dikes and sills. So I'll get into dikes and sills a little bit later. But the best kind of stratovolcanoes that we have here on Earth would certainly be Mount Fuji, Mount Hood, Mount St. Helens, and Mount Rainier. So here's a picture of Mount Rainier. This one has almost like what's called a double peak scenario at the top. And then we have Mount Fuji. So beautiful example of a composite volcano, very symmetrical. You can definitely see a lot of weathering going on, certainly a lot of snow that's being interacted here with the rock. Luckily, it hasn't erupted anytime soon. So, and then shield volcanoes. So shield actually doesn't really get a lot of attention, unfortunately, but shield volcanoes are actually quite powerful. So these are considered flow after flow constructions, which means usually a shield would have a single flow to create the shield base of it. This is why they're called shield volcanoes, is because they look like warrior shields laying down kind of deal. So you would have a single flow and it would just pretty much smooth out the shield, but then usually shield volcanoes continually erupt over and over again. And so the flow would just constantly build over and over and over again. So in that case, you would have multiple vents at the time. You could have multiple calderas. So calderas is where you would have a volcanic vent and it would just spew out all of its material and it would just collapse under the weight of how much gas and lava it just spewed out. And it could fill up again and then spew out again and then collapse again. And it could just continually do that cycle. Usually gentle sloping sides, but just very powerful. So Mauna Loa is probably the best and certainly the largest shield volcano that we have here on Earth. So certainly a lot of lava going on, but beautiful, beautiful lava flows streaming through. So Mauna Loa is very pretty. And then lava, we need to be very careful on how we determine the lava on not just Earth, but also on other planets as well. So we study the lava a lot here on Earth and come to the conclusion that it's very different depending upon your composition. And so composition and your temperature would also depend on your viscosity of the lava. Is it very gunky and very sticky, in which case you're not going to have a very nice flow going on. But if it's very runny, if it actually has a lot of silicates, also quartz in the lava, then it could be just very flowy, very runny, very watery in that regard. Molten rock here on Earth is usually filled with magnesium, somewhat silicates, but essentially you have the rock of basalt. And basalt is kind of our defining member that we have here on Earth, and then we try to define basalt on other planets. And turns out that's actually way more difficult than we actually figured out to be. But here's a piece of obsidian. So obsidian is a beautiful mineral where lava would essentially crystallize so quickly when it releases onto the surface that it doesn't have time to actually form crystals. So it essentially forms a glass. So think of like tektites, if you will, then from meteorite impacts, just the sand being fused so hot and so quickly that it practically forms that kind of a glass with it. But in this case, it's volcanic lava. So onward to space. So we're going to start off with beautiful Mercury. So Mercury, there's no vents, no major mountain cascades or anything grandeur like that, but there are pools of lava. So these lava flows are usually in these type of craters called scarred craters. So usually what happens here is that these craters would have been punctured enough times by micrometeorite impacts. And just below the surface, it would have been punctured enough for the subsurface material, viscous material, to kind of bubble up and essentially just bleed. So the craters on Mercury would bleed lava, but we call these filled-in plains all over Mercury. So the basalt, however, is not so easily defined here on Mercury. We do have some composition from the Mercury Messenger mission, which now has ended quite a few years ago now. But the basalt on Mercury is actually more sodium based. There's sodium and a lot of graphite on Mercury as well. So that's kind of giving us a bit of a head scratcher there as to like, well, how can graphite maybe change the viscosity of the lava? And then onward to Venus. Venus has the most volcanoes in the solar system. Now, whether they are active or not is still under debate. I was actually just talking to some Venus people a couple days ago, and they're all excited, like, oh, they have found an active volcano, but we need more data. We certainly need more data. But Venus certainly has a ton of basalt, a lot of sulfur based as well. There 65% of the volcanic regions of that area are volcanic plains, very similar to Mercury. But we have detected over 1,000 volcanoes, though. So, as you could see, the volcanoes, no, I'm kidding. So the problem here with discovering volcanoes in the first place, though, is that Venus has an incredibly thick atmosphere, very, very, very thick cloud layers. So it took a while for us to finally get a beautiful elevation map through the clouds. So we have, with a combination of altimetry and radar here on ground-based telescopes as well. Rest in peace, Arecibo. But we have finally our elevation map of Venus. So the pinky white areas are higher elevations, and then the darker purpley blue and some black areas are the lower areas, the lower elevation regions. So Venus is just covered with different kinds of volcanoes. There's also different types that we lovingly call pancakes, ticks, and shields. So here's our pancakes. So pancake volcanoes usually are just very bubbly, very light, where the subsurface lava would essentially just slowly push up the surface and it would just form like a little bubble. No venting or anything, no lava flowing or anything like that. It would just like a pimple, just bubble up the surface a little bit there. But we call them pancakes and not pimples, because yeah, pancakes are much better to say about volcanoes. And we have ticks, where you would have your pancake starting to form, but then what happens is that the pancake could actually get so large that it actually fractures the surface around the pancake perimeter. So it starts having a lot of these fault lines kind of stretching outward, and they look like bug legs. So we call them ticks. So it does actually look like a bug. And then we have our shield volcanoes. So this one kind of looks more like a composite volcano, but it's been labeled as a shield. So this is Mont Mons. So Mont Mons, second highest mountain on Venus. It is certainly the highest volcano on Venus. It's about 8 kilometers high. And it is based on Magellan probes. So early 1990s, comparing with the elevation maps that I just showed you earlier. So we have actually not seen Mont Mons up close and personal before. We hope to remedy that at some point. There are actually 2 Venus missions in the running for our current down select, but I'd be happy to answer questions about down selecting of missions later after this presentation. But there are 2 Venus missions out of 4 missions in the running right now. So maybe we'll have a Venus mission. Wouldn't that be grand? Because we haven't for a long time. So poor Venus, it gets ignored a lot. So onward to the moon, it's actually quite similar to Mercury in that it has large filled in plains, but these plains are lovingly called mare. So mare are just gorgeous, gorgeous regions. So just very much lava filled plains. There's no vents that we can really see, or at least not large enough vents. But we're probably thinking it's not so much of how Mercury had it, where it's just a bunch of micrometeorites and you made the craters bleed kind of deal, but more toward there might have been a magma ocean on the moon at one point. And combine a magma ocean, a very dynamic one at that at some point, combined with the tidal locking that we have on Earth. This is why we usually, what we're hypothetically thinking here, our current theory of the lunar theory going on here, is that all that magma ocean would have been brought forward on our side, the Earth side of the moon, the near side of the moon. And so if you were to see the far side of the moon, there's only like little tiny patches of mare, which we call irregular patches, is the official name. We geologists are just great with naming, aren't we? So the larger mare patches are on the near side of the Earth because of that tidal pool going on. So mare are just beautiful. Mars is certainly all over the news, especially within the past month or so now, especially with 3 missions back to back. So we had the Hope probe from the United Arab Emirates, we had the Taiwan 1 from the Chinese, and now we have Perseverance rover. So Mars is certainly just a lot of attention going on at Mars right now, but certainly a lot of beautiful volcanoes on Mars as well. So pretty similar to Earth, but the scale of these volcanoes compared to Earth are just massive, massive volcanoes. Certainly of basalt composition that we can compare here to Earth, which is fantastic. A lot of olivine this time, which is great. We have a lot of olivine with our Hawaiian volcanoes and Icelandic volcanoes. Those are the two places on Earth that we compare a lot with. Martian volcanoes as well, which is fantastic. Beautiful lava flows that can be found on Mars as well. So subsurface chambers, like I said, with dikes and sills. Dikes and sills are where you have subsurface layering of lava, and it would come up at different angles and different plumes through the surface, through the mantle, and then spout out at some point from a volcano. Most volcanoes on Mars are shield types. There's only like less than 20 in total, but again, they are massive. And Mars certainly has the largest volcano in the entire solar system. But when I say that we use Earth a lot to compare to Mars, if I were to show you these pictures though, sometimes it could get a little tricky as to like which one's Mars and which one's Earth. So in this case, Mars is on the left and Earth is on the right. And the same thing again is that Mars is on the left and Earth is on the right. But seeing the geology a lot on Mars, and then we're like, oh, that place looks familiar. Where else have I seen that? And then we can usually tie it back to somewhere on Earth. Turns out that's actually very common with us planetary geologists, is that we want to constantly find some sort of connection to a geologic feature on Earth, and then try to compare it to what in the world is going on that other world or moon. Sometimes it's not always easy. Sometimes we find geology even on Mars that we have never experienced ever in the entire solar system. We're like, what in the world is going on? But real quick with Martian volcanology history here though. So Mariner 4, 6, 7, 8, and 9, all through 1964 to 1973. Some of them were flybys, some of them were orbiters. These were the very first photographs of a whole nother planet, and also our very first remote sensors, but they all missed Olympus Mons as many times. 4, 6, 7, 8, and 9. They all missed the largest volcano in the entire system, and they all missed it. So it wasn't actually until Viking 1 and 2. So first successful United States landers on Mars. They landed on somewhat opposite parts of the planet, but we finally got our first images of Olympus Mons. So this is taken now with the Mars Reconnaissance Orbiter that's still in orbit and still fantastic with its one of the most powerful cameras in the solar system. The camera design, fun fact here, the camera design of the high-rise camera is what it's called. So the high resolution imaging camera on board Mars Reconnaissance Orbiter. That same design was also used to design the camera on Juno to make the beautiful Jupiter pictures as well. So it's sister cameras. So a lot of the same design engineering people that did Mars Reconnaissance Orbiter high-rise camera was also put on the Juno team as well. So that way we made sure that Jupiter had as good a quality, if not better, to take beautiful Jupiter cloud pictures. Anyways, back to Olympus Mons real quick. I want to point out the center here of Olympus Mons. So you notice here, it's not a perfect circle by any means. There are several divots going on here, and that's because this is certainly a shield volcano with a lot of calderas. So I believe the count currently is up to 8 different calderas. So this is called a nesting complex, is what we're calling it, though, is that, again, you would have one event to flow beautiful lava all over the shield, and then it would collapse under its own weight, and then it would fill up again and flow out lava and then collapse again, and it would just continue that cycle. So all of these different little bowl shapes that you see here are just different eruption events. Now, when they would have happened is incredibly hard to tell because lava covers your tracks. So we don't actually have a very good idea as to how old some of these lava flows are, because they constantly overflow each other and hide previous tracks. So it can be kind of a nightmare to deal with. But here's a side view of Olympus Mons. So I believe this is east. So to the eastern side, it's actually a more gentle 15-degree slope upward and then up to the base. But then on the western side is just a sheer cliff face. It just drops right down. So that asymmetric shield going on means it was incredibly dynamic in its heyday. And then also its sister volcanoes of the Tharsis region here. So we call this the Tharsis volcanoes here. So we have Arsia to the south, the middle one is Pavinus, and then the northeastern one is Ascrius. So so those three, why they're pretty much of the similar shape and similar size, very much still shield volcanoes, certainly smaller than Olympus Mons, but why they're aligned in that particular area is still puzzling us Martian geologists. So it gets interesting to see all the different kinds of theories going on. There's a Tharsis bulge in this area. So the bulge completely encompasses all of these fine 4 large volcanoes. And underneath, the crust is actually incredibly thick, much, much thicker than anywhere else on the planet. We call this the Tharsis bulge. Now, how that bulge came to be, why is it in that particular spot? It's not even anywhere near the equator. It's not really near the pole either. So why is that bulge there? Why, again, you have that orientation of the volcanoes? The current theory, and somewhat the favored theory right now, is that this is similar to a chain volcano that we would see in Hawaii. So you would have one volcano build up, a lot of lava flows, and then what happens is that the subsurface chamber would actually go, I'm bored here, I'm going to move. And it would shift over all of its viscous lava to a certain orientation, to a certain direction, and then start over again. I'm going to build here instead. Lovely volcano. Here's all of my fine lava and everything. And I'm bored again and shift again. But why did it shift in that orientation? We don't even know where it even originated. So it's that part is still a puzzle. But so far, that's kind of the favored theory amongst Martian geologists. So who knows? We'll see. But looking at a beautiful elevation map. So again, the white and pinky areas are the more higher elevations, and then the bluer areas are lower elevations. So this large scar mark here is Valles Marineris, but you see our 4 lovely Tharsis volcanoes going on here. So you can definitely see just so much dynamic going on just by looking at the elevation of this area of Mars. It's gorgeous and complex. And then to make it even more complex, here's a geologic map that we have to look at for hours on end. So every single color, every different color that you see here is a different geology. So we have copies of these maps that we have to use, and constant references to, like, what's that color again? I don't remember. But USGS gives us produces these maps for us on a nearly yearly basis. So they constantly update these maps for us. So USGS does an amazing job with their mapping department, with their mapping committee. Ceres, question mark. So Ceres is kind of a weird mixture of terrestrial volcanism and what we call cryovolcanism, but I'll talk about cryovolcanism a little bit later. But Ceres, being an asteroid, it's not considered a terrestrial body by any means because of the composition itself is different. But there is a poor little lonely Ahuna Mons, the one lonely mountain on Ceres. And so why I have a question mark here on Ceres is that we don't know why there's a lone mountain. We're thinking it might have been once some sort of buildup of might have been the start of a volcano, and then it just never quite got there. It might have just been just a buildup of material of some sort of viscous stuff. There is a lot of salt on Ceres. Salt tends to be kind of a good clue for cryovolcanism, that some sort of sticky, gooey something would have had to come about. Salt is kind of the smoking gun composition going on. So there is quite a bit of salt on Ceres and somewhat ammonia, which is also a good smoking gun composition as well. But Ceres question mark, there's actually a wonderful paper that came out just 2 years ago that I was asking the question of like, where did all Ceres mountains go? Because for all we know, maybe the mountains of Ceres either just got absolutely obliterated by impact craters, and that Ahuna Mons just happens to be the lucky lone mountain, or did all the rest of these mountains cave in and they became calderas? So who knows? Who knows? Poor Ceres, though. And then the lovely Io. So Io is getting some interesting what's the term here? Notoriety through the planetary community. So of the 4 missions that are competing against each other right now, there is an Io one, the Io Volcanism Observatory. So it's supposed to be an orbiter around Io specifically to look at all the beautiful gooey volcanoes on Io. And I mean gooey in the literal sense. They're very sulfur based. So this is a true color image of Io. So a lot of sulfur, a lot of yellow. They're constantly oozing. It's a very disgusting volcanic system on Io. But hey, you know what? It's very dynamic. If anything, it's the most dynamic volcanic moon of the whole solar system. I usually have caldera types, no mountainous structures or anything like that. It can't hold up the weight. Sulfur is so soft for lava that there's no way to form any kind of mountain. So it's constantly in just ooze and vapors. So the cool part is that we have seen a lot of Io eruptions over the years. So on the right side is from the Galileo probe from mid-1990s. And then on the right is from New Horizons when it passed by Jupiter. When New Horizons was on its way to Pluto, we decided to turn on the camera systems at Jupiter, make sure all of our cameras were still looking good and all of our equipment was still turning on, making sure that New Horizons was actually able to ping us back and go, hi, I'm still alive. I'm still in space. No worries, guys. On my way to Pluto. But it just happened to turn around and we're like, hey, you know what? We're near Io. Let's take some pictures. And Io decided to grace us with a plume. So hooray. But in reality, this is a close-up of what the calderas look like on Io. So not pretty at all. We call this scabbing as well. So it's the lava would actually harden after a while and would look like very disgusting scabs on the surface though. So Io is an interesting little moon. So cryovolcanism question mark. So cryovolcanism is still a very debatable topic. So not in the sense of debatable as in like, does it exist? Yes, it exists. But in reality, we don't actually have a clear definition of what cryovolcanism actually is. In the very basic sense, cryovolcanism is volcanism on an icy body. Okay, but to us geologists, there's a lot of debate going on as far as like, there's different types of ices. There's different types of volcanism. Would you consider geysers as a part of volcanism? The answer is yes, but there's also different kinds of geysers as well. So this is going to go through very briefly some of the cryovolcanisms that we would suspect though, but we see them on Titan, Triton, and Pluto as far as like mountainous structures go. And then materials, like I just said, what's considered cryolava. So cryolava is part of my specialty that I deal with in my research though, but I'll get to cryolava here in a bit. But we have radar images from Cassini, rest in peace Cassini, of Titan. So this is a possible cryovolcano on the surface of Titan. So you would see the central vent here. Whether it's a shield or a composite, we're not entirely sure because we actually don't have very good elevation maps of Titan, unfortunately. So this is as good as we're going to get. But the bright material on Titan here usually means that it's not, it's fresh ice. It's incredibly fresh ice. And so all of this may end up being some sort of lava flow going on. All the stripiness that you see here is not noise. Those are actually dunes, organic dunes on Titan. So Titan is also a very weird moon as well. This is Triton. So Triton actually has pools of volcanic lava. So we actually see the central vent here. At one, it wouldn't have been able to make any kind of mountains that we're aware of, but some sort of maybe impact would have started the pooling system, or this would have been a vent to start out with, and it would have just gushed outward with its cryolava, and it filled up these plains. So there's two major cryovolcanic plains here, whoops, on Triton. And then here's the beautiful geysers that Voyager in 1989 took for us. So these are of the southern hemisphere. So this picture is actually upside down. So what you're seeing here is the South Pole. But it took us a while to realize that these were geysers. But what's wonderful is that it actually wasn't that long ago. I believe 2016 or 2017, someone finally figured out the wind speed and wind direction of all these geysers and of what composition. So this is actually nitrogen geysers. So nitrogen, when kept on in subsurface levels, so we actually see this on Mars as well, but nitrogen specifically, when kept in subsurface and then released immediately in vacuum, it actually turns black. So we actually see this on Mars as well. Whenever it turns from winter to spring and all that nitrogen is being trapped in the ice, when that ice thaws out, all that nitrogen is getting released, and we see all the little black, not smoke, but just little black plumes pop up on Mars. We actually call them spiders because it's very freaky, but you see a surface completely clean of ice, beautiful winter landscape on Mars. And as soon as it turns spring, it's just all these little black spots all over the place. We teasingly call them Mars spiders, but it's actually nitrogen popping out of the ice. So it's pretty freaky to see. But then you immediately know, oh, I guess it's springtime on Mars when the spiders come out. And then beautiful Wright and Picard Mons on Pluto. So this is our latest find as far as cryovolcanism goes in the solar system. So Wright Mons is the central vent here in the middle of the image. You see all of this, what looks like knobs, and we actually do call this knobby terrain on Pluto here. So all this knobby terrain would have been parts of the lava, the cryolava coming out of Wright Mons. And then Picard Mons is this ridge to the south here. Unfortunately, Near Horizons was such a quick flyby that we did not get the rest of Pluto. So we actually don't have a 100% disk view of Pluto from New Horizons. So right at the terminus, we only got the very edge of Picard Mons and only a guess as to how big Picard Mons actually is. So we're thinking it's certainly bigger than Wright Mons, but we're only taking certain guesses. And we could tell by shadowing in the terminus and whatnot. But Wright Mons is our best guess. And then a little something I've been dealing with on Pluto is Hecla Cavis on Pluto. So Hecla Cavis is this really weird pit going on here on Pluto. So just north of the volcanoes Wright and Picard Mons on Pluto, you have this very weird pit. And it's not of impact origin because of just how weirdly shaped it is. There's actually little fissures coming out the side here. It's actually oriented in a very specific fashion compared to where the volcanism and where certain mountain ranges are as well. So I made a guess that Hecla Cavis was actually a cryo caldera at one point. So that got interesting as well. So I actually published a paper not too long ago on Hecla Cavis and cryogenic mud volcanism on Pluto. So let me clarify here. When I talk mud, I don't mean the grassy soil that will eventually get after the snowstorm season going on here. But what I mean by mud is purely by texture. So the viscosity is considered muddy. So cryogenic mud is usually meaning just how gooey can you get the ice at Pluto conditions to form the volcanoes and the cryovolcanic mud that you would see on Pluto. Because look at it this way, Pluto is about 40 Kelvin temperature. So that's about negative 400 some degrees Fahrenheit. So what could possibly be gooey at those temperatures? So it turns out it can be a mixture of certainly water ice, but that's more of your solid rock base going on there. So your rock fragments that you would get here on Earth is actually pure water ice on Pluto. But you mix it up with methane and ammonia, you're going to get some very sticky lava going on at those temperatures. So that's what I mean by cryogenic mud volcanism on Pluto. And then coming up soon, hopefully late this year, hoping, there's going to be a book coming out called Mars, a Volcanic World. I personally actually have 2 chapters that are going to be published in that book. So it's going to talk about all the different styles of volcanism that we would have on Mars, the different technologies that we've been using to study the different kinds of volcanism on Mars, and what do we plan to do in the future? You know, what is there still to learn about the volcanism on Mars? So there are a ton of questions to explore. I just came up with these at the top of my head earlier today, but I can just fill slides and slides and slides of just more questions and whatnot. But certainly some questions that we're still exploring, though, is just how can there be different flows on different planetary bodies? If you have rock and you have ice, but their flows are just so wild and so different. Lava tubes are kind of an interesting topic, especially with the moon and Mars. Could lava tubes be used to house life? And I don't mean past life in an astrobiological sense, but I mean our life. Can astronauts use lava tubes as a form of housing or a research base? Salt, goodness gracious, salt is giving everybody a headache because salt can really change up not only your viscosity, it could also change up a lot of your plume dynamics. So Europa and Enceladus, lots of salt on those moons. And it could also drive us crazy with their plumes as well. Different types of cryolava, like I said, what causes collapse of some of Io's volcanism? Why can't Io have mountains? So that's actually a current question right now. And then glass is a worry from Martian volcanism, because if we want to send people to Mars at some point, we kind of need to pay attention as to the composition on Mars. So it's not just the dust that is probably going to kill us, but some of that glass too is really interesting, and much, much more. So real quick though, I want to show you guys, if I was with you guys in person, this is typically an activity I like to do, but I'm going to show you guys rather in person. I'd like to show you guys just how big some of these volcanoes are. I'm pretty sure I stopped sharing my screen, correct? Awesome. Okay, good. All right, so going down the line here. So Mount St. Helens is my sticky note cube. So the size of my sticky note cube, this is our beautiful Mount St. Helens. So about 1,300 meters in elevation. So hello, Mount St. Helens. Right Mons on Pluto. So pretty good size comparison there between Mount St. Helens, and we're already stepping up to Right Mons on Pluto. So Right Mons is actually considered a tiny volcano to the rest of us. So pretty good jump there as well. So now we have Right Mons, and we're going to go straight to Mott Mons on Venus. So a little bit bigger at 8,000 meters in elevation. So wonderful small book. It says Astronomy in a Nutshell, by the way. I collect antique astronomy books. What year is this one, by the way? This one is 1912. So this is Mott Mons, and now we have Mount Everest. It's a little bit bigger of a textbook going on here. So Mount Everest, just a little over 8,800 meters, sorry. So Mount Everest, and then we have Olympus Mons, which is, this is the closest thing I could come up with the height of Olympus Mons. But you have Mount Everest the size of a book, and then a large size of a t-shirt, a large t-shirt going all the way up here is the elevation of Olympus Mons, the largest volcano in the solar system. Hooray. So very, very large Mount Olympus compared to Mount St. Helens, right? Tiny, cute, adorable volcanoes. All right. But that's all I really had to show you guys tonight, but I'd be happy to answer any questions you guys may have about volcanism on other planets and certainly compositions. I'd be happy to tell you about the exciting missions that are in competition with each other as well, because that's kind of our major thing at NASA. After Perseverance, this is kind of our next big hurdle to happen.
I have one. Actually, I have several. Do any other worlds exhibit, either past or present, any tectonic behavior at all other than Earth?
So that's the fun part with planetary geologists, is that we tend to take tectonics, the definition of tectonics, to be completely different. So here on Earth, you think tectonics, you immediately think plates.
Right. Plates
moving on top of an active mantle, and you have a crustal versus oceanic plates going on. But tectonics on other worlds, we use it as more of a, does the surface move? And that's our basic definition of tectonics. So say the tick volcanism on Venus, all those little fissures popping out of the pancakes and makes it look like a bug. Because it fissured like that, and because it's popping out like that, we call that Venusian tectonics. Mars has its own realm of tectonics as well, because of the bulge, would have had to bulge out the crustal system there. Valles Marineris completely shattering across the surface like that. That would have been considered Martian tectonism. Pluto tectonics is still kind of under debate, because we do see a lot of active surfaces going on, and certainly the building of right mons. But now there's kind of a debate going on as to, like, should icy bodies have a different form of tectonics because it's ice. Ice is certainly much more brittle, so of course it's going to break. But should we be kind of on our own level of tectonics? And the answer is yes, but in what fashion? So terrestrial planet people and icy body people usually fight a lot. Fun fights, fun debates. Sometimes.
If I may, I had one other question. The Sophia mission, did it not discover some water on the sunlit surface of the moon? Some evidence of water there. Is that something you get into, or are you more focused on ice at the poles?
I personally am more focused on ice on the poles, but knowing that there's water of some sort at the equator, I work on other geologic features around the moon as well. So knowing that there's water, at least in some portion in the subsurface, really changes how we see some of this geology going on, because I'm specifically working on structural geology, which means scarps and cliffs and graben, which is where the ground would form these very shallow fault lines across the moon and whatnot. So having a water base would change the physics of some of these structures. So it's awesome that they found water using Sophia, which is nice. Sophia is a beautiful instrument, but usually for farther out astronomy. So it was nice that it was utilized for the moon. And that actually happened with researchers here at Goddard. So yay, a win for Goddard.
May I ask the question? So I guess it's more related to Earth type volcanism, and it's on Mars. So Mars has about a third of the gravity of Earth, and the escape velocity is about half. So these big, I know they're shield volcanoes, or at least Olympus Mons is a shield volcano. Is there any possibility that the ejecta could have left Mars from volcanic activity?
Absolutely, absolutely. That is not a worry, but certainly an interesting concern in the astrobiological branches of planetary science, where what if you had a lot of this ejecta come crashing into Earth kind of deal. And then there's theories of like panspermia and everything like that for astrobiology. But as far as if we could tell if it came from Mars, we can do that with Martian meteorites. Mars has a very specific oxygen isotope compared to Earth. And that's actually what we do with a lot of our meteorites, is that meteorites across the solar system, every bit of the solar system has a fingerprint with chemistry. So with those meteorites, we figure out where in our fingerprint system would it have come from. So we are actually now able to figure out, did it come from like the inner, the middle, or the outer part of the asteroid belt, because it would have different fingerprints. Mars has the oxygen isotope fingerprint. The Ceres and Vesta have their own fingerprints. The moon has its own fingerprint, and so on and so forth. So Martian meteorites, there are theories as to like, okay, where would they have come from Mars? Would they have come specifically from the volcanic regions or not? Some of them have a pretty good guess based on that isotope and just the mineralogy itself. Would it have been more basalt based, in which case, yeah, it might have come more from the volcanic region, but we still don't have a very good idea as to like, was it from a volcano or was it just from a very big impact and it decided to arrive at Earth. So so that's still kind of a rocky road to go on, but who knows, maybe with perseverance and its collection of samples and core drills, it should help us at least figure out what certain samples go on.
What is the thought on how the mountains on Pluto formed? I mean, we're dealing with 11,000 foot ice mountains, water ice mostly.
Yeah, definitely water ice.
What process on a world that cold could drive mountains to form that height?
So this is the fun part, and it makes the math a little bit easier. Now it doesn't fully explain everything, because I'm actually on a team to specifically look at the mountains on Pluto. So maybe ask me in about a year.
Okay.
and we should hopefully give you an answer. But I am actually currently on a team that we're like, how would those mountains have formed?
Yeah.
But what does make the math a little bit easier is that water ice actually behaves very similar to a rock called rhyolite here on Earth. So rhyolite is a very it's softer than basalt, but it's kind of like a sister composition of basalt as far as a volcanic rock goes. We already know how rhyolite occurs on Earth, how it acts on Earth, how ductile or brittle it can be on Earth. So we're kind of making guesses as to like, cool, okay, we're gonna assume water ice could do the same thing and it out pops a mountain. But how would those mountains have formed? Because orogeny, the mountain building processes here on Earth are usually you have plates upward, you have a mountain. What we may be thinking is going on is maybe some sort of subduction may have happened. So you would have some sort of plate diving in and another plate popping out, and you would have mountains. The weird part here is that there's actually different kinds of mountains on Pluto. So now that kind of brings about a whole nother headache, is that there are different mountain shapes on Pluto as well. So the prettier mountains that I'm specifically dealing with are very similar to the Alps, very similar shape, structure, very similar to the Alps. But just a little bit to the east of those are incredibly jagged, very slopey, mountains on top of glaciers, and those are, how in
Mysterious.
the world did those form, and how did they get on glaciers?
Yeah.
So Pluto is wild.
I have to go back.
So the one mountains that you described, like the Alps, so those are converging plates, right, on Earth. And so, and you talked about, subducting. So are there maybe a couple of different processes going on?
For sure. Absolutely,
or
for
more?
sure. Yeah, absolutely. Now it's still a matter of, can we find the clues? Can we find the geologic clues one way or another as to would it have been subduction? Would it have been convergent at some point? But the mountains don't go too far. It's actually kind of a small range. So where would it have melded? For all we know, it's in a very dark area on Pluto. So even having any kind of good resolution is going to be tricky. So it's in the, if you were to see a picture of Pluto, it's in the very darkish reddish region. All that is called tholins, by the way. So it's very gunky methane. But tholins was coined by Carl Sagan to mean organic ice.
New field of study is extraterrestrial tectonics. So,
oh yeah, absolutely. Well,
yeah.
The exoplanetary community is growing as we speak. The exoplanetary community is growing large, and they're now recruiting a lot of geologic people, a lot of planetary geology people to help exoplanetary people to guesswork as to like, oh, if you're seeing this kind of atmosphere and it's like this close to its host star, and you're thinking you're getting some like silicate signatures out of it, this is the type of geology that you're going to expect out of that planet. And it's wild. Absolutely wild.
Could it maybe be the surface might be shrinking slowly as the planet cools over time? Maybe that causes the crust to fracture, and then you get things like subduction and convergence, stuff like that, possibly.
Quite possibly. We're actually seeing that a lot with Mercury. So Mercury has what's called wrinkle ridges, where it's very much like a deflating balloon. When a balloon deflates slowly, it starts having all these like little ridging on it on the surface. Mercury's doing the same thing, where the surface is compensating from it slowly shrinking, and it's wrinkling up in places. The problem though is that on Pluto we don't see these wrinkle ridges. So, but that doesn't mean it's not happening. It just means we have to look for a completely different clue. Now, what that clue could be, it's like, well, I don't know. Don't know currently, but there's still a lot of images to still pour through with New Horizons.
Well, I'm interested in hearing about the upcoming missions.
Yes. Oh my goodness. So we call this the down select. So what happens here is that NASA would put out a call for a particular program, and there's different kinds of programs. So you would have Discovery class, you would have the New Frontiers class. New Frontiers class, you would have large missions, a lot of money involved with those. New Horizons was considered a New Frontiers. Dragonfly with Titan is considered New Frontiers. It's big, it's bad, and it's going to get a lot of money. Discovery class missions are supposed to be very low cost and very small missions. And so choosing out of hundreds of missions, NASA narrows it down to usually 4 or 5 missions. A couple of years back it was 5. Now it's down to 4 missions. And they had, let's see, this was down selected last February, so a whole year ago. It was down selected down to these 4. So coming up in this May, they're all supposed to give a grand presentation, apparently virtual now, but a grand presentation to judges, usually out of NASA headquarters, but also a secret judging panel as well, so very anonymous and everything. But this panel is supposed to judge what have they done in a year to figure out what instruments they want? Did they keep under their cost cap? What do they plan to do? What are their objectives? Everything laid out. What's their orbit look like? What does their trajectory look like? What rocket do they even want to use? Everything, as if that they were already okay go. And those four, you have Da Vinci Plus, which I know sounds like a vitamin, but Da Vinci Plus is a Venus one. I don't remember the acronym because goodness gracious, acronyms drive us all crazy. But Da Vinci Plus is supposed to be like deep atmosphere of Venus, inchy plus. But it's supposed to be more atmosphere of Venus. The other Venus one is Veritas. The V is Venus, that's all I know. But the rest of Veritas is supposed to be more surface-based for Venus exploration. So you have two Venus ones. You have the Io Volcanic Observatory. So that's going to be the Io orbiter. So that one's going to be really interesting. And then you have Trident, which is going to be a orbiter for Neptune and Triton.
Wow.
So that one's I'm kind of hoping for. I'm biased because I work on ice, but but all of them have had a year. And May, June is when we're supposed to find out who the finalist is, and then that mission is good to go, and they get the funding and they get to be an actual mission and join the leagues and join the ranks. So we're all kind of in like betting pools now of like, oh, I wonder who, who's gonna do what and everything. I know people on every single mission, so I'm like, oh no, my friends are all competing against each other. I'm not on any of them right now, but it's like, oh no, none of my friends are talking to each other because they're all each on different the missions right now. Just it gets very intense.
Volcanism's been around on Earth for, I guess, 5 billion years. I mean, since its inception. And Mars had it and doesn't have it. Is that related to the mass of the planet and the pressures, the temperatures generated by that extra mass on Earth as opposed to Mars? And if so, would that not suggest that Venus would likely be active?
So the interesting part about Mars as to why it's no longer active, it's still definitely a debate. A lot of volcanologists with Mars call it the pre-Hellas and the post-Hellas volcanism. And now there's becoming a debate as to like which volcanism would have been pre-Hellas basin versus post-Hellas basin, because now we're wondering if whatever caused Hellas basin would have helped slow the core down. And when you slow the core down, you're essentially cooling your mantle. When you cool your mantle, there goes your volcanism.
Right.
It's kaput. And so there would have been active volcanism that predates Hellas basin. But some of those volcanic flows and whatnot are very old, very, very old volcanism. There's a couple of volcanoes near Hellas basin that are pretty well preserved, and they're called Hadriaca and Tyrrhenia. But those volcanoes show a completely different volcanic system than the Tharsis region. And so maybe volcanism pre-Hellas versus post-Hellas would have been wildly different based on that heat. Post-Hellas would not have had much heat, but maybe a completely different composition going on. You would have had differences in the atmosphere as well. Ancient Mars would have been very wet, maybe even warmer, but current Mars now is incredibly dry and very, very cold. So your composition would have done a complete 180 there. So that would have probably affected the lava flows. It would have affected your structure of the volcano. It just would have changed everything. And there are compositional eras. There's geologic timelines on Mars, but we also have a compositional era on Mars as well. And one's more what we call siliceous, or also just more silicates involved, more quartz, more of the lighter minerals, more aluminum and nickel-based compositions. That would have made the lava very runny and very flowy and very watery in a sense. But now you have more iron, more magnesium, really gunks up the pipe works in volcanism. So that volcanism would have been way more explosive, but way more sticky as well. So in terms of Venus though, oh goodness gracious. Yeah, Venus volcanism, I'm not entirely sure if Venus volcanic people and Mars volcanic people are really talking to each other, because they get into a lot of debates as to like, you know, could we really compare the two? Whether Venus is still volcanically active is still very much under debate, because it has an incredibly slow core as well, but the heat is still very much there. The basalt is very strong, very strong with the force on Venus in that regard. But there are bright radar spots that we see on some of the tops of volcanoes, and that's kind of a good clue that they are at least fresh. But are they fresh with lava, or are they just fresh mountaintops? And that part is still like, we don't know.
The flows would show up, wouldn't they, in the radar?
The flows might honestly be very tiny, very tiny, that radar wouldn't be able to pick them up. If you have a very large base and then a very nice big flow, then yes.
Maybe.
But they're thinking big base and just little tiny trickles that it would not be able to show up on radar. But unfortunately, with Arecibo being gone, we can't really do any round 2 observations of those radar signatures. So
is that where most of the work was done?
Yeah.
At Arecibo?
Yeah. Some work was done with the Greenbelt telescope, but the Greenbelt telescope radar systems are very low resolution. So they were used as more of a component with Arecibo, but we may end up just having to use Greenbelt as our prime telescope, at least until the.
What about the VLA? Wouldn't that have better resolution?
Probably not with radar.
Oh.
They're really good with radio, but radar systems, I don't believe VLA has been really used all too well.
Is Arecibo S-band? Do you know what frequency it runs at compared to Greenbelt?
Yes, S-band and I believe K-band.
K, okay. So, I mean, the resolution at S-band is not that great. So the reflectivity is, I mean, it's not going to show that. At that distance, it's not going to show features.
No.
Small enough to figure out what's going on with the bright spots.
Right, exactly. Yeah. So if anything, it's just truly like, there's a bright spot. But seeing radar bright spots gives us a little bit of an idea of like, oh, good, something is fresh somehow on the surface. But is it from volcanism, or is something snowing? It does snow metal on Venus. So could it just be snow capped mountains going on Venus, and that we're just seeing a fresh deposit of metal snow?
Chaff. Radar chaff.
Yeah, exactly. So but now the problem though is we're not entirely sure what metal would cause such bright radar systems. So there are actually Venus labs in the nation. One's at NASA Glenn. My friend is in one of the people in the Venus lab there. Let's see, where else is there? Los Alamos in New Mexico, I believe, has a Venus lab. And then Germany has a Venus lab as well. So they all talk to each other. Venus is incredibly dangerous to deal with in the laboratory. I was fine doing Pluto in the lab, but Venus, oh no. Oh no, you do not want to do Venus in the lab.
Well, why not?
It's essentially a bomb. So that's why. So imagine a piece of equipment, usually this tiny. It could get a little bit bigger, but you try not want to get bigger. But pressurized to about 90 bars pressure, and seal it enough so it doesn't have any contact with oxygen, and you completely pressurize it and fill it with gas up to 90 bars, usually with sulfur dioxide, and then you heat it quickly up to about 900 Fahrenheit. Or
simulating Venus conditions. Yeah.
Yep.
Yeah.
Yep. Yeah. So very much a very pressurized hot container of sulfur dioxide.
How do you simulate Pluto conditions at 40K?
Much easier and, and I wouldn't call it safer per se, because you can get immediate frostbite if you're not careful. And also you deal with some carbon monoxide as well. So asphyxiation is also a problem as well. But whenever I was in my Pluto laboratory, certainly before the pandemic, so getting it down to that cold of temperatures, you would have to do something way colder than liquid nitrogen. Liquid nitrogen would just freeze on the spot, just immediately solid ice cubes of nitrogen. So what can you possibly use to make it colder than liquid nitrogen? Is liquid helium.
Yeah.
Yes, liquid helium. So down to liquid helium we go. You would only use a little bit because liquid helium is very scarce.
We're running out of it, so don't use too much.
Nope. So I designed my lab to actually have a recycling system. So very, very small leakage. You only have to refill the system once a year, actually. So so it has a very nice recycling system. So it uses that liquid helium to its full extent. And yeah, it could get down to actually 10K temperatures in my laboratory. But my chamber, very nice shiny chamber kind of deal, didn't get down to 10K. And then microbar pressures. So right now on Earth, we're at 1 bar pressure. So microbar pressure, nearly vacuum of space. You would use a very simple system of using a vacuum pump, a very, very loud system, but it essentially sucks all the oxygen out of the tank, and it keeps it essentially pressurized. So it's considered an ultra high vacuum is what it essentially creates. So nothing comes in and nothing goes out.
And how do you simulate? I mean, what's inside the chamber that you?
Oh, right. Okay. So inside this grand chamber, we have what's called a cold finger, which by all means we have done all the James Bond Goldfinger puns you could think of. Oh yeah, we have the theme song and everything in the laboratory of Coldfinger. So it does look like this little metal finger inside the chamber. And what happens is that's where all the cold, everything just kind of vaporizes onto it. So what we do is that we mix our gases. We have carbon monoxide, nitrogen, and methane. Those are our main gases on Pluto. Mix them all up at different ratios and different combinations, different abundances. And we essentially vaporize it into the chamber through a little small pipe kind of thing, but we pressurize it inside. As soon as it pressurizes inside, all that gas is going to immediately be drawn to that cold finger because that's the coldest spot in the chamber. And it immediately forms an icicle. So with that icicle, we can learn all sorts of stuff. So I specifically did near infrared spectroscopy. So you have this beautiful icicle hanging down and you shoot not a laser, because a laser would actually melt your ice sample. Some of our labs, other labs that I've dealt with, have accidentally used a laser before. Oops. So we've learned not to use lasers. But you can use near infrared spectroscopy typically uses a flashlight system. So this light would flash its light onto the surface of the icicle. That light will bounce around inside the icicle. Those photons will bounce back into a sensor. That sensor will get fed through into a laser. Now the laser comes into play. That laser will see how diffuse the light is. And that diffuse light will then give us a spectra. And all the pretty little lines and everything can tell us okay, this line tells us there's methane. This line tells us it's nitrogen. There's no line for carbon monoxide. Where did the carbon monoxide go? and it's a very fun puzzle.
Huh.
So imagining looking at these lines hundreds and hundreds of times, that was my whole PhD. But hey, it worked. But learning about carbon monoxide is my pride and joy. You wouldn't think carbon monoxide is like, whatever. It's carbon and it's oxygen. How exciting can it be? Hardly anything has been done with carbon monoxide at such low temperatures because it's a very dangerous chemical by all means.
Is that one of the key components of the tholins?
No, that's methane. That is methane and irradiation. So Georgia Tech is actually doing a lot with Pluto tholins, and San Antonio, Texas has a beautiful lab working specifically on Pluto.
That's responsible for that reddish area on Sharon, isn't it? The tholins, yeah.
Yes. How it got there at the pole is still to be determined. Why is it only in that one spot? We're thinking something would have smacked into Pluto and just kind of went pop on top of Karen's pole.
Could it have leaked from Pluto?
Yes, but we just don't know in what capacity and why only in that one spot. Yeah, so it's Pluto's weird. Pluto's weird. Carbon monoxide is weird, and oh goodness gracious.
Well, any other questions?
Is there any evidence of ongoing volcanic activity on Mercury? Because we think Mercury has a molten core, but it's kind of an oddball having such a small planet with a molten core. But is there any evidence of ongoing volcanic activity on Mercury?
That's a very good question. As far as I'm aware, yes and no. So those wrinkle ridges with Mercury slowly shrinking, we're thinking those wrinkle ridges may be a good clue as to like, good, there's got to be still some sort of viscous something underneath the surface to still make the surface crinkle like that. If you were to just have a surface just automatically break, that's all it's going to show is a fracture. But it's not showing fracturing. It's showing what like dragging your hands across a bed sheet. It's wrinkling up. But you got to have some sort of surface, a soft surface, for it to wrinkle and not shatter and brittle and break and everything like that. So in some capacity, there's got to be some sort of viscous subsurface, but to the extent of filling in craters like it used to, and pooling and bleeding, essentially, probably not to that scale, or at least not recently. Then again, we haven't really been back to Mercury. Messenger's been dead for quite some time now. By all means, if we have another mission to Mercury, that would be great. But unfortunately, Mercury is not getting attention, at least not much anymore, unfortunately. So give it another 10 years and maybe Mercury will come back into like, we got to go to Mercury.
It's hard to get there, so, and survive.
Fair enough. But I mean, you know what? We haven't been to Venus, so.
That's true.
You talk about a hard landing. Yeah. How long did the Venera missions land last on the surface? Like 15 or 20 minutes?
Yeah, I think the longest may have lasted like barely 2 hours.
Yeah.
I think that was like Venera 16, I want to say.
That's a pretty good accomplishment, 2 hours in those conditions.
They were big. I just learned how big Venera probes were. They were nearly 2,000 pounds. So
Really?
Perseverance is just over that weight, and it's the size of an SUV. I didn't realize how big the Venera probes were.
Wow.
Someone asked me the other day, like, yeah, the Venera probes would have like hard landed on the surface. I'm like, really? I thought they were small. 2,000 pounds? Oh, yeah.
I'd love to know how they landed them.
Down.
Well, I mean, parachutes in those conditions wouldn't work very well, I wouldn't think.
I think they had retros.
Retros?
No, that makes sense. Yeah.
Yeah, it would have to, that mass. Is Pele, there's an active volcano, for better words, on Io, called Pele. Is it constantly erupting?
That's a good question as well. So I believe it's Pele, and there's another volcano named Loki.
Loki.
Loki was one of the
God of
original ones to be
mischief.
named. Yep, because it did give us mischief. So aptly named. It was a volcano that kept cropping up and then disappearing and then cropping up and disappearing, and so aptly named, it was called Loki for that reason. Whether they're still active, we currently do not have any cameras on Io right now. Juno is supposed to have an extended mission, but it's going to specifically look at Ganymede and Europa, but it may do some quick flybys of Io. So hopefully, but Juno right now is still going through Jupiter orbit, but it's going to extend out its orbit to encompass at least Ganymede and Europa. So that'll be really nice because Ganymede is gorgeous and highly ignored as well. I'm going to be doing some Ganymede work all through March, actually. So I'm jumping ship from the moon and going to be on Ganymede for a while. So hello from almost Ganymede.
Awesome.
We call it planet hopping. So I'm planet hopping. Just last week I was doing Mars. This week I'm doing Moon. Next month is all Ganymede, and then I'll be back on the moon. So all over the place.
Someone else have a question? I thought I heard someone. I must have heard a noise. Okay, any other questions? Now's your chance if you're interested in ice and volcanoes.
I just want to remark before we close out.
Somebody was muted, I think.
Okay,
Daniel?
Daniel.
I think you're still muted.
No, he's unmuted.
He's unmuted, but I can't hear him.
How about this?
Yes.
Oh, yes.
Okay. I have my mic and stuff set up for my virtual desktop for work, and whenever I do Zoom on my local desktop, it gets all messed up. Anyway, I guess a more fundamental question is: so you mentioned that we don't know how long Olympus Mons has been the way it is. What would it take to determine that? Like, will we ever know, or what's the deal with that?
So the best way to do it would be to take core samples at different lobes of lava. So the cool part about Olympus Mons is that there's different lobes of lava, and you could see kind of where they intersect, but they go like every which way. And so it would be cool to get like little core samples or rock samples at each lobe, and then you can pretty much just date the rocks.
Okay.
Based on the isotopes and everything. We can't do that currently with our orbiters right now. We've tried so much spectroscopy. We know all the dang composition, but that doesn't really give us a good idea as to
Gotcha.
like the age.
Okay.
Yeah. So we're gonna need some rock samples at some point, all across the volcanic region. And that would be wonderful to have, but for now all we have is just pretty spectral cameras looking at it going, yes, it's basalt. Thanks. Thanks, Mars Reconnaissance Orbiter. I didn't suspect that at all.
So we just need Elon to send somebody there to go drill for rocks then and get samples.
One-way trip for volcanic rocks. Good luck finding a volunteer, but who knows? I shouldn't
Right.
question things anymore. I see a puppy. Hi, puppy.
Ah, yes, there's a puppy.
Astro dog here.
Aw.
Are there any other questions from the people on the Zoom? I don't see any hands raised. I don't see any mouths moving, other than Amy just did something. She's laughing. So I would like to say that you were a very dynamic speaker. I really loved. I think speaking for all of us here, it was a very interesting talk. I can't wait to have you back after you publish. So, or just send us a link to your paper if you can't get to us, because I'm sure the press is going to be calling and things of that nature. And you'll be really busy with giving presentations. Hopefully COVID will be over and you'll be able to go to symposium and have a good time. So I'd like to thank you on behalf of the Evansville Astronomical Society and the members of our Facebook group. And then turn it over to Chuck to close us out here, if you don't mind, Chuck.
Yeah, Caitlin, thank you so much for joining us. And I would love to have you back to talk about Pluto sometime, because I'm really interested in that. And we'll arrange something in the near future, hopefully, because you were great. And thank you for fielding so many questions as well.
Thank you guys so much. I really appreciated the invite, and I can't wait to come back. You guys have been an awesome audience and awesome questions too. And I'll definitely keep you guys up to date. I'll let Chuck know, and then he can disseminate the information to you guys on any cool stuff that we find at NASA and anything volcanism, and certainly Pluto and all the weird mysteries going on in the universe.
That's great. Thanks again, Caitlin. Really appreciate it.
Yeah,
Thank
thank
you.
you.
Take care.
I'll send you a link
Thank
to
you.
the YouTube channel once I post the video from tonight.
Great.
Good night, everyone.